Hello and welcome to a new session of the Saturday Night Live show. Today we'll learn about Apache Spark and how to use it for pre-processing the data at scale before we use TensorFlow for predicting some analytics on the data. We'll be using TensorFlow version 2 and we'll learn about the estimators APIs, how to use them for fast predictions and model training and deployment. Let's get started. So I believe you can see here the screen. I'm enlarging the font so that you can see it clearly. So I have shared with you this file so that you can follow along and code along with me.
I have it pulled up with you.
Yes, if you follow with me along the coding, that gives the best experience. All right.
Yes, I've saved a copy in my drive, so I will follow along with you with my copy.
Good, very good. So what is the plan for today? The plan for today, we start building a boilerplate TensorFlow configuration, how to check for the GPUs, how to make sure that the CUDA is enabled in the code and so on. And then I'll start the same operation for Apache Spark, install Apache Spark, install the Java development kit, make sure that Apache Spark plugin for Python can access the actual Apache Spark library. And then we'll be having a classification project, a simple project for classifying the tumors in some readings from medical image diagnosis software, and the data is available on Kaggle and is available also on the UCI repository datasets. So we'll be using these data, which is numerical data, and then we'll be learning how to normalize the data, prepare it using Apache Spark, and then export the normalized data so that we can read it using TensorFlow 2 dataset APIs. And from there, we'll build TensorFlow estimators. These are high-level canned estimators that we can use out of the box, one line or two lines of code, and they are highly optimized for production and deployment. So that's kind of the high level over the high level APIs of Keras. So, and it allows you to deploy the models to TensorFlow Hub and so on. And then we learn the APIs for the estimator, the create APIs, the train, and the evaluate. Finally, I will show you how to connect the visualization from TensorBoard with the TensorFlow estimator. And then I'll show you how to export the model for production, which is done using TensorFlow X servings. I'll not dive deeper into the TensorFlow X servings or the servings API, but I believe it is one of the things that require a lot of attention because it optimizes the production workflow, allow you to deploy models in real time without any downtime. And there are different deployment policies, and it is extensible as well, so you can optimize it using your own C++ code. It's very interesting, and it has a very sophisticated architecture. I recommend at the end of this session, you take some time to look it up and see how to figure it out on your own. So these are the topics we cover. I've already told you a brief introduction about these topics. So let's get started. So first of all, we can directly load the TensorBoard extension, but it requires that you have already TensorBoard installed on your machine. So here you load extension TensorBoard, and then import TensorFlow as TF, and then run the code. It'll take a few moments to run.
I was able to run that, by the way, in case you were waiting for me.
Sorry, I was just double checking on Slack to see if somebody is trying to connect and having difficulty, sorry. And then it has completed running here. My apology. Because sometimes maybe there is a difficulty in connecting. Because last time when we did this session, there were kind of 15 attendees, but then I changed the form for registration, and this is what we get. I believe they are trying to connect and it's not possible. Do you think so? Maybe we can send a reminder. Does it add to your calendar when you connect like this, Gidon? You are muted.
Yeah, there was an option to add it to my calendar, which I did. And so I have the link to the meeting that I can put into Slack.
So I assume everybody who has registered has already received the same calendar, right?
Yeah.
Just to make sure that everything is fine. You should have received now an email from Zoom. Have you?
Not from Zoom, from AI Institute.
Okay.
Oh, but it is from Zoom, yeah.
Okay. So I have sent an email, again, confirmation, just in case somebody is missing. But as I said, let's continue now. Sorry for interruption. So my friend, everything I do now is kind of boilerplate configuration so that I am very sure I'm having the right versioning and the right tools enabled for me, such as the GPU and CUDA. So we start with tf.version. I think Raj is sending. He cannot connect. He sent on Slack. Sorry for interruption again. I will send to Raj so that he can join. So we have just started. We import TensorBoard, and then we import TensorFlow TF, and then we double check on the versioning. Which version of TensorFlow are we using? And then we double check, are we really using the eager mode or just the graph execute, the static graph mode? So I need to check that the tf.executing eagerly. They will return a Boolean. So I double check whether the eager mode is enabled or not. And that should be enabled by default in TensorFlow 2. And then I double check for the GPU, tf.is GPU available. And if it is not, I need to check to enable the GPU from the runtime. So next, I can also list the devices of the GPUs, how many GPUs are available for me. Sometimes you have more GPUs. So you need to be aware of their of configurations of your hardware. So tf.config.list physical devices will give me such configurations. And then finally, I can say tf.test.isco-built to SCUDA. This will let me know whether my system has SCUDA enabled or not. Usually when you're setting your servers and you're doing the setup on your own, these configurations make all the difference, because sometimes you assume that you have GPUs, but when you run the training, it's very slow. So you need to be sure that the GPU is enabled, the GPUs, how many GPUs you have in case if you have more, and then whether you have compiled the system with SCUDA or not. Here you can see we've got GPU is true, and then we've got one GPU, the CPU 0, which is the CPU, and then we've got the another CPU, and then another, here we've got the GPU, and then I assume it is one GPU, physical device GPU of 0. I think this is more like XL GPU. We need to double check what that is in the internals of Colab, but it's again GPU 0, and we've got both CPU and XLA CPU, GPU and XLA GPU. So I assume that's all in order now.
It is for me.
Yes, very good. Thank you, Jidon. So next, we move on to the autograph and set the verbosity to 0, and the get logger and set level to error. So why I'm doing this, I want to silence the logging from TensorFlow, because TensorFlow estimator is very savvy and consuming when it comes. I will find it very hard to keep track of what's happening. So tf.autograph set verbosity to 0 will, and then get the logger, the default logger for TensorFlow, and set the level to error will silence the logging. So let's do that. If you don't want to do that, you can skip this one, but I don't recommend it for the sanity and to keep your workspace clean. And since we are using TensorBoard, all the logging will be going to TensorBoard anyways. So next, I will install the OpenJDK for Apache Spark, and then I'll download the Apache Spark 2.4.5 from the official repository, and I will extract the file, and then I'll install the Find Spark and the PySpark packages. So what I'm doing here is 3 things. I need Java runtime or Java development kit. I need Apache Spark library, and I need Apache Spark wrapper for Python. You need 3 things. And you need this one as an extra utility, Find Spark, so that you can connect the Python wrapper to the actual Spark. I'll run that. And after running this one, if I navigate here on the left to the runtime, It should start printing, listing some directories here for Apache Spark after unzipping them. So I can see some attendants have joined us. In case you are not following with the exercise, let me share with you the Colab file so that you can code along, because the point of the live coding is that we can code along together and you can follow on using the same file I'm working on. So you can make a copy and start working on that. So you can see here on the left, it is downloaded the zipped version, the archived version of Apache Spark, and then unzipped it. And if I open it, you can see the different libraries and the GDKs, examples and jars and so on of the Apache Spark itself. So by double checking on the XLA, the one we've got when we expected the device here, XLA CPU and XLA GPU. This XLA is the optimized linear algebra compiler for TensorFlow 2, one of the accelerated linear algebra models, and this is very specialized compiler, and it's designed and benchmarked for fast speed and memory optimization for TensorFlow calculations. So I believe it will fly in production. Now that we have got Spark, let's set some environment variables, the Java home, and this is the directory for the Java on the Colab, and which I have just installed, and then the Spark itself, which is available under the content right here. I believe the content is relevant. You can remove this one since I have it at the root level to be more accurate. But since I've got fine Spark anyways, it doesn't make a big deal for me. So starting from here, I really need now to connect and initialize my code. So to initialize Spark, I will import find Spark, and then I'll run find Spark.init. That will initialize find Spark. Since I've done that, now I can safely import PySpark. And then to get a Spark session or Spark driver, I'll just type down Spark equals PySpark. Since I will be working with morely the SQL context, so I will get the SQL context from the Spark session by typing PySpark SQL and then Spark session. Because you know Apache Spark, it has the Spark session, which includes Spark context, and which includes SQL context, which includes Hive context. So it's kind of nested context. I am interested in the SQL because I'll be working with that and the CSV files, data frame APIs. So I will get the Spark session, I'll get the builder, master, and since I'm working on local host, I will say, okay, local, any IP for local, and then singleton object. So I say get or create if it doesn't exist. One object, a singleton object. So I've got here a typo, local. I run that again. For the attendants who have come here, I can see a few attendants have arrived. Eleanor and Emmanuel, welcome to the session. Please, is the voice clear and you can see the font on the screen? Please let me know. So next, I'll be running my global variables. I'll set the batch size to 1024. I can set any other batch size. I can use a cross validation to optimize for the right batch size. I will set this one as a starting value. And then I'll set how many training steps I want to work with. I'll set it to 64. The training steps is the number of the size of the data set divided by the batch size. So if I have a data set of 1,000 images, for example, and a batch size of 32, I divide 1,000 by 32 and use the result as the number of the training steps. I can do it more than that, or I can do it lower than that. This is just an approximate value to work with. And then for the validation steps, I can set it to lower value since I've got a smaller testing set. Then the number of epochs, I will set it to 128. Then the learning rate, I will set a moderate to small learning rate, such as 0.002. For the shuffling, I need a buffer. So the buffer I will set here is 128 as the buffer space or the buffer pool. So I can buffer the data. I can shuffle the data as I'm loading them through the Tensorflow to Dataset API. And then I'll run the code. This is supposed to do the. So I run the code, and after I run the code, now I have set some global variables, and then I will be able to use them along in the rest of the project. Just interruption for a moment here. I can see there are attendees who cannot join the session, saying authorized personnel only. So for those who have attended, how have you managed to log in? I can see in the chatting, voice is clear, thank you. It's clear, thank you. Okay, thank you. So I'll start here my project. This is the data set I'm working with. I'll start with the breast cancer Wisconsin University dataset. So this is an open dataset for breast cancer diagnosis, and it has the readings collected from medical imaging software, and then they have been manipulated for us to make the job easier. And then as per the citation request, so this data set is obtained from the University of Wisconsin hospitals, And here is the citation. And it's also available as a public dataset on kaggle.com and on the UCI repositories. So if you want to reference any of these two, you can find them easily. What I will do now, I have uploaded the CSV file to GitHub repository so I can download it easily. In the next project, next week, I'll be working with more Kaggle APIs to show you how to download Kaggle data directly into your Colab and use them and submit results for Kaggle as well from the TensorFlow, from the Colab. So I can now inspect the data. I can say, okay, head of my data, which is breast cancer data.csv. I can also inspect the tail of the data or the count of the number of data. I use the exclamation mark so that I can run the Unix commands, the terminal commands, as in the desktop applications. And the WC count, word count, -l, count the lines, and then the same file. That should count the number of samples in my data set. So you can see right here, it downloads the file, saves it in the root directory, and then I can see here the first few rows from my data set, and then I made a typo in the counting. It's dash, not underscore. Download it again and override the old one, no problem. You can see the data are all numeric data, and then I've got an ID, which is a serial number, and then diagnosis, which is malignant M or benign B, but it's not here in the head. I can see that in the tail. And then I've got the numerical geometric data extracted from medical images. And you can see clearly here, I've got 569 rows in my data. So next, I will be working with Apache Spark and use it to pre-process the data and balance and sample the data and split it into training and testing split. So I'll say Spark because I've already created a Spark SQL object, and then read CSV. That's the simplest data frame APIs available in Spark. Allow me to work with spreadsheets and CSV files like this. So I will pass the name of the file. And then header equals true. And then infer schema equals true. So I'm just instructing the data frame API to be aware that the header is included. And then infer schema, most likely you need to pass the schema as explicit schema so that it can use the explicit schema object to map the fields or the columns to the right data types. But you can also safely use the infer schema so that it will map these columns to the data type inferred implicitly from the data available in the spreadsheet. Each one has its pros and cons. I would say if you want to programmatically manipulate the schema, then you can use the schema object and define it on your own. If you want to keep it the defaults and carry on with your project, then you can allow infer schema. Hi Raj, I can see that you have managed to join. Sorry
Hi.
for the problem.
No. I had few issues on my system, so it took a while for me to figure it out. That's fine.
Okay. I believe many of the attendees who are registered for the session are having the same problem because
Yeah.
it requires you to register and then it requires you to sign in to Zoom before you
Yeah.
join.
Yeah.
I see. So this is the file we're working with. I believe
Yeah.
you have already got this file. Let me
Can
double
you
check
please
you
can you
again.
please share it again? Yeah. Thank you.
Yeah. So you can follow along now to everybody.
Okay.
So try to carry code along with us in this session so I can get the most out of it. We are here at section data pre-processing with Apache Spark, okay?
Okay. Sure.
So now I have read my data frame into DF object. So I can run the statistics, the mean, the average, the minimum, the maximum. All I need to do is type down df.describe. Remember, Apache Spark works in a pattern called transform action pattern. So I describe is a transform, but to get the actual values, I need to do an action, which is collect. So transform is description, will calculate the statistics, but it will only done once I collect this data. Because Apache Spark uses lazy loading pattern, it does not carry any executions of any calculations until I have already requested these results. And then you can use pprint, which is pretty printing. So pprint is a method that allows you to print in the command line a nice formatted data. So I will use that to print the stats I've got and see what kind of data I am getting after this operation. Here you can see I'm getting a row, which is a structure, a data structure from Apache Spark. And this every row I've got a summary. The summary here is a statistic value I'm calculating, the count, mean, standard deviation, the minimum, the maximum, and so on. And then for every column in my data set, I'm getting the summary for that column. For example, for the texture mean, I'm getting the count. For the radius mean, I'm getting the second value we said is the mean itself. It may be confusing for you because the actual columns, they are named the mean value from the geometrical data, but note that it has nothing to do with the statistics we are calculating. Why I'm doing this step? I'm doing this step because I want the mean and the standard deviation for normalizing the data, or I also want the minimum and the maximum for doing the same thing. So I can either use minimum maximum scalar, or I can use standard scalar for normalizing my data. So next, I will be creating a dictionary of these statistics I have calculated so that I can use them for the further pre-processing. But I need to skip some values so that it does not clutter my workspace. These values, starting with the summary column itself, I already know which column I'm working on. I mean, I'm interested in the mean and the standard deviation, so I can skip that column from the stats data frame, and I can skip the ID because I already don't use it in my further analysis. And then for the purpose of normalization, I will only normalize the features, so I can ignore also the diagnosis or the classification result. You have observed here at the end of the data, there is an empty column, a dummy column, C32, which is in the files because maybe there is a comma at the end of every line that we need to skip. So you can safely do this and remove this one as well. So now I have defined which columns I want to skip. I will now be iterating over the columns in my data and creating a dictionary for the features and their summaries. So I will say for row in stats, what I need to do, I know that now I can use the method from Apache Spark called asDict or asDictionary. So I can say for key comma value in row dot asDict as dictionary dot items. So as dictionary will convert the Python, the Apache Spark row structure to dictionary. And then because I'm in Python, I say items, this will return the key and the value so I can loop over them. So next, I need to skip the column and double check if any of these keys is already in my skip columns. I'll say fk in skip columns, then I will continue. So I don't include it in my summaries. So I'm interested in the mean and the standard deviation. If you want to do the minimum maximum scalar, then you can do frow dot summary equals mean. So this will filter the data with the mean. And then what we need to do next, we can say means. I've already created a dictionary at the top, means dictionary, add the key, and then equal the value. So what is this doing? Is this appending the mean value for every feature under this dictionary, which I've created at the top. Also, Jidong and Raj, feel free to unmute yourselves. It's okay if you want to interact.
Also,
if you want to
I've
ask.
been able to follow along.
Okay, good. So we've got the means, the standard deviations, the skip columns, and everything taken care of. Now we need to do the same for the standard deviation. So I will use elsef row.summary equals standard deviation. Then in this case, I will add the standard deviation to the dictionary so that I can use it further. So standard deviations dictionary of the key, which is the feature name, and the value, which is the standard deviation of that feature calculated from the previous step. Then I can use the pretty Brent, bprint, for the means dictionary to inspect it visually. And I can do also the pretty printing for the standard deviation dictionary. And let it run. You can see here I'm getting for every feature the mean value and the standard deviation value. I will use that in the next steps. But so far what we have done, we have loaded the data file using the CSV APIs, and then we have calculated some statistics, the mean and the standard deviation for every feature of our data frame. You could have calculated the minimum and the maximum if you want to use another pre-processing. Hi Igor, I believe you have the file from last time, but in case you don't, I will share with you the live notebook in the messaging, and feel free to unmute yourself if you want to ask questions and interact. It will be very nice.
Whoa.
That's nice music. So I have shared the notebook I'm working on with you on the messaging here in Zoom if you want to code along so that you can get the most out of this experience. So next, after this, I will be using some features from the SQL, the Apache Spark SQL interface. So I will create this command, df.create or replace temporary view, will create a table that I will run SQL queries on from the data frame df. And the name of the table will be diagnostics. And it is temporary, I mean it is not global, not shared across all the nodes in the cluster, so I can run my queries in this node on my own. And after I'm done with this, that temporary table will be removed from the memory, leaving no clutter behind me. So I want to find out how many benign samples are in the dataset and how many malignant samples are there. So what I can do is use the query as if it is a SQL database and run spark.sql and then select count from the table I've just created, diagnostics, where diagnosis equals B. So B here stands for benign. And then I can do the same for the malignant cases. And I can say spark.sql. I say select count as if I have a SQL database. One of the nice features about Spark, and also works in Spark streaming and runtime to get aggregations about the data as they arrive into your system. We will have a session on Spark streaming as well. So I select count from diagnostics, where diagnosis equals M, which stands for malignant. You may wonder, can I just do the counting using other methods like filter? I can use filter and then count. Yes, you can. Of course, you can. There are many ways to do the same thing, and that's why it is robust. As I told you, the Apache Spark is transform action pattern and the lazy execution. So it will not execute the query itself until I give it an action like first to collect the data. And since I've already run this query before, I know the number I'm interested in will come as index 0. Since I'm only querying a single value, the count, I will do the same here, first of 0. Now we need to inspect our results, so we can print them to the console. Brent number of benign and number of malignant. So we've got a typo somewhere. Let's get back and see. Select count from. So indeed, we've got a typo here. Select count from where.
Is the parentheses, I mean the quote mark on the M.
On the second line, yes. Thank you, thank you. Double check. Here we go. Thank you, Jidong. So we've got here the numbers 357 samples for the class benign and 212 samples for the class malignant. So we can observe our data is not very balanced. It's almost imbalanced. So you can see here, we need to take that in consideration. We already had a module on imbalanced data set and manipulation. So we've seen some techniques like undersampling and oversampling and manipulating the objective function. In this case, for this exercise, I will keep it in my processing. So now in the next steps, I will need to do a train test split of my data. I need to convert my column, the malignant and benign, from letters to numbers, zeros and ones, so that I can work as a binary classifier in TensorFlow. So since I'm debugging in this column, I need somehow so that if I'm running the same block multiple times, it does not generate an error. So I will do a check here, F label, the column I will be creating in the next lines is in df.columns. I have already created the column, then drop the column since I am debugging, and I use the command drop, df.drop, and add the label. Then kind of the same condition, but the opposite. I'll say if label. This is all for the sake of debugging, nothing in particular. If label not in df.columns, which will always be the case since I've just dropped it, just double checking on myself so that it does not throw an error. So I will now import another tool from Apache Spark Machine Learning. I'll say from pyspark.ml.feature, I'll say import string indexer. So this is a pre-processing module available in features of PySpark, and that will convert any string into an integer. So now I need to create an object of the string indexer so I can use it later for fit transform. I will say pyspark.ml.feature.string indexer, and then I specify the input column I want to convert it from a string to integer, which is the label column diagnosis, and then the output column I will just name it label. This way, every value in the column diagnosis will be converted to a binary value in the column label. So the benign or malignant will become 0 and 1. Next, I will applying some fitting indexer model object.fit over my data frame. So this will study the data frame based on my input and output columns, and then we'll have the model that can be used to transform these data. So fitting here, we'll go through all the data, count them, see the unique values, and map the unique values to integers, but it will not actually apply the transformation until I use the transform method by running indexer model.transform. And then we add the df. So next, now let's do some exploration of what we've got so far. So I can actually run Brent of what are the available parameters of this model. I'll just say indexer model dot explain params. I can also print out the labels I've got so far. I can say print indexer model dot labels, so I can see what I've got. If you observe here, I've got the input column, the output column, and some other invalid handling parameters. For example, whether I want to keep invalid values or escape them or fire an error. You can see it's all here. I can keep or error or escape. And finally, I've got my labels. So the B becomes a 0, the M becomes 1. So we can be now sure of what we've got. Also, the ordering string order type is by frequency. So it's by default frequency ascending or descending or alphabetical. So you need to be aware of these parameters so that which one is assigned the index 0. So the default one here is the frequency ascending. So I can be sure that the majority class is the index 1, the minority class is index 0. So I have already run this one. Now my job now is to do train test split. I want to split my data into training and testing data. But first, I need to make sure that my training and testing splits, they have the same number of samples respecting the original ratio in the original data. So that process is called the stratification, meaning I am splitting my data, but I keep my ratio. So what I can do now, I will show you another way to filter the data by the column. So I can say df.filter and then df of diagnosis equals B, and that will create a data frame that has only the samples that has the label B. And then I can do df.filter df diagnosis, and then I can do for the other class or category with the label M. So now I've split my data into two data frames. Each one has only pure data from either of the two classes. So now if I split my data, I'm sure now that for every data frame I'm splitting, I'm having the same ratio as for every class in my data, either benign or malignant. So I can do that using df_b dot random split, and then I can specify the weights for my split. I can say weights equal 0.65 and 0.35. And then I can do the same thing for the other class. I can say dfm dot random split, that's for the malignant class, and then I can specify the weights, and then that will be 0.65 and again 0.35. So I've split my data from pure splits of the samples into their pure categories in data frames. So I have train test splits that are each 65% of the original data, but then they are pure. Train is only benign, train M is only malignant. Now I need to merge them back so that I can start using them for training later on. So how I can do that? I use the method union, a set operation available in Apache Spark. So I can say train b.union, train m, and then I can say test b.union test m. So this will merge the two data frames into one data frame back again, but this time they will be respecting the ratios I already started with. Not sure if it's not scrolling again. Let me refresh my screen so that the scrolling works back. Okay, now it's scrolling again. Good. Can you clearly see the font? Just let me know if you don't. So next, what I need to do after I split my data, I need to save that into onto my desk so I can load it from TensorFlow. I also can now print my data. So I can say train df.count, and I can say I think it's got too big. Let's minimize it a little. Okay, then I can also say test df.count. Nothing fancy, just counting the number of rows in my new data frame. Since I've created some columns in the I save it on desk, so I'll say train df.drop. Observe here, I'll be using the operator asterisk. So I explode the list which I print next into arguments. I can just say the actual arguments and separate them with commas like ID, V32, and then diagnosis. But if assume that you are working with a list and you want to type and you have many columns, you don't want to type them down, then you can use the asterisk operator and the list operator, and that's exactly the same thing. I'll do the same thing for the test df, and then I can drop again the ID, V32, and diagnosis. Finally, I'll be saving my files on disk. I'll say train df.repartition. This is important since there are as many partitions as number of cores on your system. If you have 8 cores or 4 cores, then you have as many partitions. The file will be sharded into these clusters or nodes. And then because it's a multi-distributed system or multi-threading or multi-processing, so you need to repartition, bring them all back to the same machine before you save them. This is not kind of the best practice, but since we are working on the one machine already, so we don't want the file to be scattered into small scrambles, we can just say train df.repartition1. That will bring the file to one file, and then I say write.mode overwrite so that it overwrites the file, and then for to save it as CSV file, I need to specify the option so that it saves the header file of as well. And then all I need to do is CSV and pass the name of the directory. Let's be consistent with our naming here. I'll see this one. Let's use the same name I'm using here. Make it smaller a little. I think it's freezing again. So I'll be using the name of the directory as diagnosis-train. And then I need to do the same thing again for my testing. I pre-partition again to one node, write, and then set the mode to overwrite so that it does not throw an error if the file already exists. And then option, I set the header to true. And then the CSV, a diagnosis dash test. So far, so good. So I can just, for sanity check, make sure that everything is running all right. I can use os.lestdir method. And run my code. It should print all the files in the root directory. You can see here I've got diagnosis test directory created and diagnosis train. If you go to the left side, coding, inspect the diagnosis test, for example, you find it has one part, and that's named hash code, and then at the end the .csv file. And the same for the training. It includes one file and the end CSV file. So if you don't use repartitioning and assume you have a quad-core system, then you will have 4 files like this instead of only one. So to start using TensorFlow, we'll be reading these data and importing them into the TensorFlow dataset APIs. So I'll start by inspecting the file names, since now I'm moving as if I'm moving to another system. So I will, as if I want to programmatically make the file's name, since they change from run to run because it's based on hashing. I will use now the module glob. Allow me to list the files and filter them. I'll say glob.glob, which will list the files under directory. I will say double star so that it searches into nested directories. And then I will say star or asterisk.csv. I want the CSV files inside the nested directories. And I will specify the parameter recursive as true so that it searches subdirectories as well. And then I will print my files list. So I've got here my CSV file, the original one. I've got here the testing file, and I've got here the training file. Since the hash changes from different runtime to another, I will be reading that using a for loop from this list. So I will start in the next block with an empty file name. And then I will loop over. I'll say pattern in files list or file path in files list. I will look for every element in this list. I'll set my training CSV file. So I will check first if there is the word train or diagnosis-train in the file path. If diagnosis-train in FP, then I say train as CSV is FP. And then I will say if diagnosis-test in FP, then that FP now I'm sure it is my testing CSV file. So I'm picking the file name from this list, the list printed above, that contains these small patterns like training and testing. So what I need to do next, I will print these data such as train CSV. I'll add a new line just to make sure I've got the right file. Hi, Sean, how are you?
Hi, Mustafa. I'm good. How are you? Sorry I'm late.
Feel free to unmute yourself and I'm very well, thank you. Feel free to unmute yourself and turn your camera on if you like.
Okay,
It's
thank you so
interactive
much.
session.
Okay.
So make sure you can follow
Okay.
the file I'm sending in the chatting right now, the updated version. So here, this is the Colab file I'm working on. You can
Okay,
start working on
I
it.
can see it.
Follow
Yeah,
along.
appreciate it.
Okay, thank you.
Yeah, thank you.
So now we're sure we have the right training file and the testing files. Let's move on and then load the files using the Tensorflow API. So I'll be using the command tf.data text line dataset. Flow is that there are many ways to do the same thing, makes it very robust and very powerful, but sometimes makes it confusing. So for example, since this is already a CSV file, I can use the CSV module from tf-contrib. I can use the experimental CSV reader from TensorFlow 2. I can also use TensorFlow datasets from TensorFlow X or extensions. There are many ways to load the CSV file. I'll use the most straightforward one, text line dataset, as this is the one built into the dataset APIs. But using other ones is equally all right, no problem. So I will be reading the dataset once into the training set and the other into the testing set using text line dataset and start saying test CSV. I run my file. So it runs now. So I need to inspect the data. How does it look like? Make sure that I got the right data. I'll say for line and train set. Let's take 3 rows and Brent what we've got. Observe here, we've got here the header file. Are you sure you want to work with the header file inside TensorFlow? Most of the cases, you want to take the header file and use it for feature columns, which we'll come to explain next, because feature columns is one of the essential ideas for both TensorFlow estimators and the TensorFlow deployment. But let's say that I want to skip that for now for my processing. So I'll say skip 1. And observe another thing here is that TensorFlow Dataset API is using the same map reduce or map filter pattern from Apache Spark and other distributed system libraries or lazy loading libraries. So you can see I can do and map many pre-processing operations one after the other, as you can see here. I will become very clear once we go to the pre-processing method with a lot of maps. You will see what I'm talking about, as you can cascade as many functions as you want on top of the dataset adapter. So because we will be working with feature columns, as I've said, we need to extract the column names because these are our features, and then use them as a parameter for the TensorFlow estimator later. So let's actually extract the data from the first row. So I will just say, okay, use the list task casting, and then take the first row from my data set. And then since this one will return a batch, I will say square brackets index 0 of the list so that I take the first one. Even though my batch is only one element at a time, but still you need to extract that element using the square brackets of 0. So since this is a binary data, you need to convert byte code, byte data, or byte string. You need to decode it back into string. You can do that simply using the variable you have just created, and then convert it to NumPy. Now it's a NumPy value. You can simply decode it using UTF-8 Unicode encoding. So now this will convert the byte code here to actual values that we can work on. And then I'll say string dot split by comma. This will split the features names into separate fields that I can work with. And let's print that to see what we've got. So you can see we have got here the column names, the features names from our processing. So far, so good. Let's now do some boilerplate preloading of our data, so I can also discover and explore together the robustness of the TensorFlow APIs. So I will say train set dot skip. That will skip the first row, and then I use this backslash so that I can continue writing code on the next line. And then I say dot shuffle, and then I use the buffer as the global variable I created above, so I can easily run multiple versions of my notebook and find the right hyperparameters. And then I can repeat. So there is also a method named shuffle and repeat. So how many times I should repeat my data? I should repeat as many epochs as many steps. So number of epochs times number of train steps. And then I need to batch the data into batches, so I can use the batch size I defined above as 32 or 64, it depends. So this will do some boilerplate loading of my data out of the box without a lot of effort on my end. I still need to do the same thing for the testing. So I can say test set dot skip the first column, the first row. I'll do the same thing, but I will change the number of repeats. So I will shuffle. So shuffling allows me to get random data every time I iterate over the data set with an iterator. So allows me to train my model on unrepeated data as much as possible. And then I can specify validation steps. And then I can batch my data as batch size. And run my code. So this now has run. Let's inspect the result. How does it look like? So you already know this command very well. I'll say for batch and ds for dataset train. Let's take 3 batches. And then let's print the shape of the batch object. And run my code. So you can see I've already got batches of 1024. And for every batch, I'm not getting the number of columns. So that's what I will be working on next. I will be decoding the CSV using decode CSV method from Tensorflow IO so that I can convert the string rows into features as separated by commas as I've just done with the column names itself. So let's see together how this works. It's very intuitive. So I define a method preprocess that takes a batch similar to the batches I am getting here in the previous step. And then I need to specify the column types. I leave it empty so that TensorFlow will figure that on its own. It's very similar to Apache Spark when I said explicit or implicit schema so that it can allow Apache Spark to infer the schema on its own. So this is a similar idea. I can see a lot of similarities already between TensorFlow and Spark and similar distributed systems because TensorFlow is designed for production, deployment, and distributed processing itself. So I believe it takes advantage of all these different paradigms under the hood. And then I can specify the length of my columns, which I've extracted manually in the previous step. Over here, you can see I've extracted ds underscore columns to be the feature names. So I can safely say that the data types is empty objects as large as the number of columns I'm having. And then I can say tf.io.decode. You can see I've got a lot of decoding functions. So I'm interested in decoding CSV. So I will be passing the batch and the record defaults for the column types. So the batch is coming as an input to the method. And the record defaults the data types. If you want to specify the types on your own, be my guest, go ahead. I think it is safe to leave it to TensorFlow to decide. And then the output is columns. So decode CSV, what it returns, if you want to print the output and see it, it will be for every feature, it will return a vector for that feature. So instead of returning row-wise data, it returns the data as column-wise. So what you need to do is to transpose the data and stack it together again. So I will see tf.transpose to convert the rows instead of the columns, and then tf.stack so that it puts all the columns together as one data set. So I'll say columns. But which columns? I want to skip the label column because I want to return that on its own. So I will say for all the columns from 0 up to the length of ds of columns -1. So I'm stacking all the columns returned from the decode CSV except for the label column or the category column or the diagnosis column. So what I will do with the diagnosis column, I will use it alone. I will say tf.cast. I'll be casting it to integer 64 since it is just a binary classifier. Which column? The last column, index -1. And then what casting I'm working with? tf.integer 64. And then I need to return my x, y. This pre-process function will extract the features, put them together, and return them. So let's test, see what this looks like. So I'll say for x, y, and ds train map pre-process to take 1. So I can say Brent x.shape, y.shape. So what I'm happening here, I'm mapping the training set and applying the pre-process function to every row, to every patch in my data set. And then I'm taking one batch for inspection. Double check my shapes, double check my values. Let's first double check the shape and see how it went up. So I've got the batch size 1024, and I've got 30 features. And this is in line with my prior knowledge about the dataset. It has 32 columns. 30 of them are geometric features, and 2 of them is the ID, serial ID, and the other is the diagnosis column. So that's in line with my prior knowledge about the dataset. So what does it look like? I can just say print x of 0 and y of 0 to have a look at my data. Maybe I still need to do something else. I can see my data. There are different ranges for the data, so maybe it's time to normalize the data. And my y data is either 0 or 1. Can you see my y data? Where did it go? Here. You can see my y is 0. If I try another one, because I've already got a large batch, so I can try the last one. It's already shuffled, so I expect to see some randomness in my data. So yes, here is 1 instead of 0. So I can see different ranges already a little bit different. So let's normalize our data. I will use a standard normal, but you're encouraged to use minimum maximum scalar or any other that you believe will lead to better accuracy results. So far, everybody, are you following along and coding on your end? Jidong, how is it going?
Yeah, I was able to follow along. I'm where you are right now.
Okay, very good. Raj?
Yeah, I'm able to.
Sean, how's it going?
Yeah, me too.
Okay, very well. Igor, are you following? Are you coding along? Igor Zadda. Hello, are you coding along with us? You can type in the messaging, you can unmute yourself. It's an interactive session, feel free. And also feel free to ask questions. Okay, no problem. So we continue with our discussion here. We are now going to pre-process our data. So I will create a list, an empty list, and that will be the same order as my feature columns. So in this, I will be collecting the means and the standard deviations, which I've already created in the previous step from Apache Spark. And you can use the same thing for the processing in a desktop application or on server side. So the idea that you can communicate this data from Apache Spark to TensorFlow, you can use RESTful APIs, you can store it on disk, you can cache it in memory, but at the end of the day, you can access this data because you have already done that pre-processing somewhere at some other time. Either synchronous or asynchronous processing. So I can say for column and DS of columns, which I've just collected. And then I will skip the label column. I don't want to normalize the label. If column equals label, let's continue. And then I know that I have already stored the dictionary of the features with their means, so I can say ordered means list dot append, and then I will be casting to float the value from the means dictionary from the very previous steps when I was doing Apache Spark. So that I will extract the mean value by feature, because it's a dictionary of feature and the mean. So it's a dictionary. I can pick the value using the column name. I say means dictionary of column, cast it to float, append it to this list in the same order as my data appears in TensorFlow. And then I'll be doing the same for the standard deviation. I will say, okay, ordered standard deviations list dot append, and then float, and then standard deviations of dictionary of that column. So now I have two lists. Each list has the same order as my features. One list has the means and the other has the standard deviations. Now let's go ahead and normalize our data using this knowledge. So I will be now converting this means list to tensors so I can use them inside TensorFlow. And observe that I cannot do this outside the this method, because I want my graph, which will be constructed internally by TensorFlow automatically for me, to be internal to the same graph. I don't want to do discontinue or disconnect my graph. So what I will do, I will say tf dot convert to tensor. And what value am I converting to tensor? The ordered means list. And what data type I'm using? I can say data type equals tf.float32. And then I can do the same thing for the standard deviations. Say tf.convert to tensor. I can say ordered standard deviations list. And then I say dtype tf.float 32. So now I have the tensors. I can use these tensors directly because they are in the same order as my feature x. So I can just say z, which stands for z-score or standard normal, is x minus means tensor divided by standard tensor. That's all it takes to do standard normal. And then I can say return z comma y. Now I have normalized my data. So let's inspect what does it look like. So I will say for x comma y. Now we have already memorized this very well because we have done that multiple times. I'll say for x comma y and ds train.map. Now you can see the powerful APIs of TensorFlow 2. I can map preprocess, apply preprocess to every batch in my dataset, and then I can map normalize, apply that to every batch that in my dataset after I have preprocessed it, applying CSV decode, and then I can apply take one, so I can take one batch and expect it. Let's see the shape. What does it look like now? X.shape and Y.shape. So it is the same like before. I have not touched on that. Let's inspect the values, see if they are looking more normalized now, standardized. So I can run that now, and you can see the values, they are more around 0 with unit normal. So they will be centered around 0, and the further will be unit distance or unit standard deviation. You can see we are already respecting that range either in positive or negative. Here you can see it's a little bit beyond the unit, but that's okay. It's a standard normal distribution. Of course, you need to apply unit testing to your data and some other double check verification to make sure that you're doing things right. So let's see one of the other things that we can do magically with these APIs. So I'll write now a method. This is just for sake of curiosity. And then I will use tensorflow.math.reduce mean. I'll say x comma axis equals 0. And then standard deviation tf.math.reduce standard x comma axis equals 0. So this way I can calculate the mean and the standard deviation over the batches. So this is kind of batch-wise statistics, not over the whole data set, only over some batches. And since my batch size is relatively large, I can find some agreement between the mean and the standard deviation on the batch and on the complete data set. So this is the idea, just for curiosity, and then I return the mean and the standard deviation. This one is just for exploration. So what I can do now, I can now loop over the mu and the standard deviation returned from ds_train.map the preprocess, and then map Instead of applying the normalization, I will be applying the stats method. And then I will take one sample for inspection. And then I will print the mu and the std. So just for comparing an apple to an apple, I will be doing the same which I've done above. tf.convert to tensor of my ordered means list and specify the data type tf.float, so I can print each side by side and compare them. And again, tf.convert to tensor, and then use ordered standard deviations and d type equals tf.float 32. So now I can print the means tensor and the standard deviations tensor. Let's see what we get and compare the values, see if they are matching each other. Of course, you need to visualize better than expecting visually like this. So the first one is 1.4. The first one is 1.4. The second, the 9.6. The second is 9.6. Here is 1.9, 1.9. For the standard deviation, 3.5, 3.5, 4.2, 4.3, and then 7.7. Here is 5.2. You can see the difference is not really huge, but this is just for curiosity. I wanted to double check whether the mean overall, the global mean and the global standard deviation, are really respected in the batching on that scale or not. So now you know, if you didn't know, the larger your batch size, the more consistent or related your statistics to the overall statistics of the larger data set. Next, I will be working with feature columns. I'll say, okay, let's now convert our data into feature columns. So to convert the data to feature columns, we need to create a features dictionary. We'll define a method, make dictionary, that will be triggered over all the batches of my data set. So I will say features equals an empty dictionary using the dictionary object. You can also use the curly brackets. It's the same. And then I will be applying a for loop over all the features and the values from my X and Y. For example, I can just say for feature, comma values, and zip ds of columns, which remember the string, the list of strings for my feature names, and I'll say from 0 to -1, except the last one for the label. And then I need now to unstack my columns because I just need to associate these columns with the dictionary. So I will say tf.unstack. Instead of stacking in a previous step, now I'll be unstacking them again because I just need to map them as the key, the dictionary, the feature name, and the column, the feature itself. Remember, this is kind of redundancy. You may say this is not efficient, but we have already stacked them together to do some pre-processing and normalization. Now we need to use that for another purpose. So I can use unstack. And remember, the objective here is to explore as many APIs from TensorFlow as possible. So it is safe for illustrative purposes. In production, be careful what you're doing because that will increase the operations in your pipeline and reduce the efficiency of your pipeline for prediction and for training as well. So I'll see tf.unstack the features x along the column axis equal 1. And then now I can iterate over my data. I will say for each feature, I'll create now a dictionary. The name is the feature name, which I already got from the list of strings. I will replace any spaces because some features has spaces in the name. I will replace that with underscore, and I will assign the values. And then I will return the features and the labels. Now this step is done. Let's see the result, how it looks like. So I can say for batch, comma labels, nds train map preprocess map. You can normalize or not normalize, but for inspection, I will just call make dictionary directly. Take one. And then I can do bprint batch.keys and print my work. Let's see how it looks like. So you can see here, I've got dictionary keys, the feature names. So that's already a dictionary. And if I inspect the values, you can see I have got the features, each one in its own column. And then for every feature, I've got 32 of these. You can see these are 30, I mean 30. And then for each one, I've got 1024 values for all the samples in my batch. So again, this is keys are features, values are the actual features values in my data set. A batch dot okay, it does not, this one does not support comma like this. So again, now we know what's happening. So we need to create the actual feature columns. So I will create the feature columns as a list. I will say for feature name, remember why we are using feature columns? Because feature columns, this is an efficient way to tell TensorFlow to actually load the data in production and know the types of the data efficiently in runtime, and also store that and process that efficiently either in memory or in caching. So for feature name, in DS columns from 0 to -1, I will be appending a feature column value. For this example, it is simple because all our features are numeric features. So I can say tf.feature column dot numeric column. There are embedding columns, there are categorical columns or one-hot columns. The more we explore in our projects, the more we cover of these different feature column values. The whole philosophy, the concept behind feature columns is that you want to make your pre-processing and predictions in one model instead of having to do the pre-processing in, for example, in pandas, and then doing the actual predictions in TensorFlow. Now it can all be done all in one place in TensorFlow. So results in better deployment, better production environment, and often better speed in prediction. So I can say the name of this feature. It has to be consistent with my previous steps. So I can say feature name dot replace any spaces with underscore, comma, and then I pass the D type. I'll say tf.float32. Always double check your work. After you have completed this one, let's print the feature columns. Here you can see we've got a feature column, numeric column, the key, the shape, the default value or default data type, and normalizer function. You can even add the normalizer function here instead of doing it before. So you can see this is a very powerful API. So starting from here, we'll be working with the actual TensorFlow estimator. So we'll cover 3 or 4 types of estimators and how to work with them and connect that with Keras. But it's almost 2 hours now of continuous coding. And we continue next time starting from TensorFlow estimator. All right. Do you have questions?
No questions, Mr.
Okay, so far what we have learned is how to pre-process the data using Apache Spark, extract some statistics, split the data into train and test split, and how to handle imbalanced data sets for the train test split and do stratify or stratification with Apache Spark, and then save the data on disk. And we have learned how to load the data from disk with TensorFlow 2, read the data with the TensorFlow dataset APIs, pre-process the data with map function, and convert the data using tfio.decode CSV to decode the data, and normalize it using the statistics we have learned in Apache Spark. And finally, convert the data to feature columns. Feature columns are the format that TensorFlow estimators understand. Feature columns allow us to have the pre-processing of the features and the prediction and the training all done in the same environment, in the same model, without having to use multiple tools for that. Unlike you load your data first, pre-process the data with pandas, and then run the prediction. In production, this will increase your pre-processing overhead. So we have learned now how to use the feature columns. And next week, we continue with the actual estimators work and see how we can go on from here. I hope you have enjoyed this session as much as I've enjoyed your company. Thank you, Raj. Thank you, Jidong. Thank you, Sean.
Thank you very much.
Thank you. And
Thank
see
you,
you next
Mustafa.
week.
Okay, see you next time.
Yeah.
Bye.
See you next time.
Yeah.
Yeah.
Bye-bye.
Have a good weekend.